Professor Jim Gibbons. Jim is, of course, well known to everybody in the room, and so I will be brief to give him more time to talk. Jim finished up his PhD in electrical engineering and then spent some time at Cambridge on a Fulbright scholarship before he came back to Stanford to join the electrical engineering faculty. He started the solid state laboratory, one of the original ideas that led to integrated circuits and the things that we've been talking about all day. He did some really pioneering work in the field of ion implantation, understanding the physical basis of it, modeling it, and so on, that has lived on to this day. And then he became Dean of Engineering in 1984, and there's a whole long list of things that Jim accomplished when he was Dean, and I'll just mention two or three of them. Whenever I think of Jim's term as Dean, the very first thing I think about is the fact that Jim was the person responsible for bringing the computer science department into the School of Engineering, and in many ways I think that transformed the engineering school here to this day. Jim also started the STVP, or the Entrepreneurship Program, which continues today and has had a lasting and very important impact on providing an education in entrepreneurship for all of our students in engineering and beyond. He oversaw the building of new buildings for both the computer science and the electrical engineering department. The Packard building and the Gates buildings were things that Jim worked very hard on when he was dean. And finally, he was one of the people who brought the concept for the Center for Integrated Systems to fruition. And that building and the people that were in it were really the basis for the revolution that took place in semiconductor technology, computer systems, and so on that we've been talking about today. So in many ways, the foundations that Jim led as dean continue to this day, and they really remain the foundations of the School of Engineering and the Electrical Engineering Department today. So please join me in welcoming Jim Gibbons.
I noticed that Stephen just comes up this in one bounce. At my age, you don't do that anymore. And I have an observation to make. If you have any choice in the matter, don't let yourself be giving a talk right behind Tom Lee. That's because he's funnier than you are. And unfortunately, you may be in a situation, as I am, where you have to disagree slightly with a part of what he said. We'll see how well you guys buy this. So my title is Bill Shockley and John Linville, Silicon Valley and Stanford EE, 1955 to 75. I want to take you through the history of that period. And I want to note at the outset that without the agency of Bill Shockley and John Linville, I think things would have been vastly different than they are. I'll try to prove that to you. This is my point of slight disagreement with Tom. There are a series of very pivotal events in 1955, and I want to go through those one by one. The first one is that Fred Terman, then the dean, not using the EE faculty to help him choose who to hire, decided that the EE graduate curriculum at Stanford needed transistorizing. So he, believing in his instincts, as he should have, hired John Linville. It was an extraordinarily far-sighted appointment, as it turned out. John's job, as his appointment papers show, was to transistorize the EE graduate curriculum. That's where it started. So John offers the first Stanford graduate course on transistors and active circuits, the name also of his book, in the winter quarter of 1955. First pivotal event in 1955, I claim. He also created a lab where PhD students could use transistors in advanced circuit designs. I was a member of that lab. The second pivotal event in 1955 was Maury Tenenbaum and co-workers at Bell Labs, who announced the first fully diffused junction transistor through a publication in the Journal of Applied Physics. Silicon transistors had been built before, but they were by a crystal growth technique primarily. And this was different. This was something that had the potential to scale, and Shockley knew it. So he saw the great opportunity in this development. He left Bell Labs 5 weeks later to start a company that would use the diffusion process to commercialize silicon bipolar transistors and other semiconductor devices. He then, like all entrepreneurs do, starts looking for funding. It didn't fall out of the sky, you know, by a previous arc transmitter or something like that. Sorry, Tom. Unlike most events today, most people looking for money today, Shockley concluded his funding effort in 4.5 months because he found Arnold Beckman, himself also an entrepreneur, and by then a very well-off one. And so he got his funding from Beckman, and he promised Beckman, some of these things are in red here. I've taken them from Shockley's notebooks. So they are quotes from the Shockley diary, not in every case, but mostly. So he promised Beckman he's going to build the most creative team in the world for developing and producing transistors and other semiconductor devices. He succeeded in doing that. He didn't get advantage of it, but he succeeded in creating the team. So then there came a little altercation between Beckman and Shockley about where the company should be. Beckman, of course, wanted to be in Pasadena because that's where the headquarters for his company were. And Shockley wanted it to be in Palo Alto because his aging mother lived at 949 Waverly Street, still there. They compromised on Mountain View. Shockley always won. He rented, with some help from John Linville, a Quonset hut at 391 South San Antonio Road, 2,255 square feet at 5.5 cents a square foot. The first home of Shockley Semiconductor. There is the Quonset hut. It's hard to believe that the foundations of Silicon Valley came from there, but modest circumstances are often the best. Shockley's office was in the right corner of this, and if he was in town, his Jaguar coupe was right next door to it, and if you were well behaved, he'd give you a ride in it. First ride was often enough. He then, having money in a building, had to put people in it. So after a series of very careful searches and reading lots of papers and talking to lots of lab managers who had worked with the likes of Bob Noyce and Gordon Moore and so on, he hired something like the most talented team he could find to help him achieve his goal. Bob Noyce, Gordon Moore, Jay Lass, Jean Herney, Sheldon Roberts, Vic Greenwich, Gene Kleiner, and Julie Blank. 4 PhDs in physics in that group of 8, 1 in chemistry, and 1 in electrical engineering. That was Vic Greenwich. He'd been a student of Dave Tuttle. I knew Dave Tuttle. Probably most of you guys don't, but anyway. He was an extraordinarily good teacher. He had 2 PhD students. One of them was Vic Greenwich, and the second one was Dick Pantel. For quality, that's as good as it gets. So the team assembled in April of 1956. The team assembled in the Quonset hut and began to develop the basic technology for fabricating silicon bipolar transistors. Lacking an equipment supply chain, the group has to build most of what it needs. Then, in the fall of 1956, Shockley does something that is usually a no-no for startups. He abruptly switched the company's principal focus to the 4-layer diode from the silicon transistor for telephone switching applications. I'll explain that a little bit later. But inside the labs, inside the Quonset hut, Noyce and Moore are arguing for silicon bipolar transistors as the first product, and then follow that with the 4-layer diode, if it's still had a future. Now we come to a piece of Shockley's management style that is well known, but maybe not in the personal way that I happen to experience it. It turned out that persistent difficulties in building the 4-layer diode led Shockley to berate individual employees in open meetings, trying to communicate to you what the emotional state of the team was. The best analogy I can think of right now is that Shockley predated Donald Trump by 60 years in his willingness to use the phrase, "you're fired," in public situations. That was Bill Shockley. For reasons that are unexplainable, Shockley allowed the junction transistor team to continue to develop diffusion technology for silicon junction transistors. Now, a little respite from the anxiety that the team was feeling. Shockley learned on late night, November 1st, 1956, that he, along with John Bardeen and Walter Brattain, would receive the Nobel Prize in Physics in December of that year. He's overjoyed, of course. So he throws a champagne brunch the next day for his team. Here they are. I'll just identify these guys for you. On the lower left is Gene Kleiner. Next to him across the table is Gordon Moore, then Sheldon Roberts, then Vic Jones, who didn't hang around too long because he had an appointment in the Harvard physics faculty, and after he came out here for a short while, he decided that Harvard might be better. There's Bill Shockley, the happiest look I've ever seen on him. And from the right on top, that's Jay Last, Vic Greenwich, Leo Valdez, Bob Noyce, Julie Blank, Jean Herney, and Smoot Horsley. 5 weeks later, the senior team is writing a letter to Beckman to complain or explain the intolerable working environment. That letter ends with, "Please help us immediately." Signed by the senior team, except Bob Noyce. So, next day, December 10, or second day after, Beckman comes up to meet with the team. They have a proposal for him. The proposal is, you should focus this company on silicon transistors only. You should appoint a new manager, and we'd like to ask you to find a place at Stanford for Shockley so he can still serve as an advisor. Stanford, of course, knew nothing about this. Beckman appeared to agree with the team, but after discussion with Shockley, decided to make no change. Now, John Linville enters the story. He was on the first slide by being brought here to transistorize the curriculum. John thought, what does transistorize mean when Shockley's starting a company in Mountain View? So he talks with Shockley about the possible impact of semiconductor technology on the education of EE doctoral students. Shockley's position was that Stanford should have a laboratory where students could build devices as part of their PhD research. After some discussion about how they might do this, Shockley offered to train a faculty member that Stanford would select to build a lab on campus where students could fabricate experimental devices. Now, March '57 is another pivotal year, or pivotal results at least. By then, Gordon Moore had created a repeatable process for fabricating high-quality silicon diodes in the Quonset hut. He believed the lab was within a few months of having a silicon bipolar transistor. He was right. But they weren't going to do it under Shockley's roof. Shockley, now 75% of the way through his funding, moves Jay Last, John Herney, and Sheldon Roberts to the 4-layer diode team and puts extreme pressure on everyone to succeed. Same month, John Linville got a small $35,000 contract from ONR to set up a semiconductor processing lab at Stanford, never before attempted in the electrical engineering department. And as it happened, I was offered a faculty position in EE with an initial half-time apprenticeship to the Shockley labs to learn there how to build things and set up a lab here. Mid-May of that year, deteriorating finances at Beckman caused Beckman to visit Shockley Labs to tell them to please keep expenses down. They were easily the most expensive operation he had. Shockley bridles at this request, stands up in this open meeting, says, "Arnold, if you don't like what we're doing here, I'll find new funding and take my team somewhere else." And he walks out. Shockley. The next morning, with the team huddled around him, Gordon Moore calls Arnold Beckman to say the transistor team will not follow Shockley anywhere. Beckman again, to his, he regretted this in his later life, but he again chose Shockley over the team. Then, Moore et al. Realized that their bridges were now burned. They prepared individually to try to find jobs for themselves individually. Sort of in one last gasp, in July of 1957, the group met at Gordon Moore's home in Los Altos, 1474 Alford Drive, actually. They realized that between them, they possessed all the expertise needed to make silicon transistors using diffusion technology. They'd done it. They decide to leave as a group to go to a new company that wants to build silicon transistors as a group. They also decide to keep up appearances of full-time work at Shockley while they're looking for backing. I arrived for my first day at Shockley's on August 1st. After taking the necessary exams, I'm told that Bob Noyce will be my device coach, Gordon Moore my diffusion coach, Jay Last my materials coach, and Vic Greenwich my circuits coach. Not bad mentors. I knew none of these people. They welcomed me, and I have no idea that they're intending to leave in the very near future, 6 weeks later. My coaches. They had retained Bud Coyle and Art Rock at Hayden Stone, an investment firm in New York City, to help them find this company that would see in them a terrific opportunity. They couldn't find a company, but they knew Sherman Fairchild, and they explained this, what the opportunity was to him. Sherman Fairchild at the time was, first of all, the founder and CEO of Fairchild Camera and Instrument, and the largest single personal shareholder of IBM stock. Fairchild offered the group a contract, $1.4 million, 18 months, with additional funding given satisfactory progress. And Sherman Fairchild wrote for himself an attractive buyout agreement in case this thing was going to be successful. The group, to commemorate this, showed up in San Francisco and signed $1 bills in Rock's office to commemorate the event, and I believe one of them is in the permanent display at Intel. I haven't seen it, but I think I've been told it's there. September 18th, 1957, the team individually resigns. They hand in their letters of resignation to Maurice Hannafin, who was then the manager. The next day, September 19th, 1957, they signed the agreement to form Fairchild Semiconductor Corporation. That is the birthplace of Silicon Valley. That's the birth notice for Silicon Valley. Silicon Valley's got a way to go to become Silicon Valley. Shockley, to his everlasting credit from my point of view, honored his promise to Stanford to set up a lab. So the way that worked was, I was working on getting the lab going, and working with Gordon, et cetera, as long as I could. And when they left, Shockley said, okay, your coaches are gone, but I'm going to help you. And the way we're going to do this is we're going to meet at Kirk's. Kirk's was a hamburger joint then. It still is in Town and Country Village here. But then it was up El Camino, just a little way from where Arastradero crosses El Camino. Shockley loved hamburgers, and that's where you had lunch with him if you were going to have it. So we would meet and for an hour. And first thing he wanted to know was, okay, Jim, how are you going on the projects that you're working on for me, not the lab? Well, because I was, one of my assignments had been to use the 4-layer diode in some sensitive military applications where it was ideal for the application. So that's what I was doing for him. And 10 minutes or so from the end of the hour, he'd say, okay, what's going on in your lab? And I'd tell him, okay, here's the problem I don't know how to solve. And sometimes he knew how to help me. Most often he didn't, but he knew people that did. And more than likely, he would call Morgan Sparks, who had taken Shockley's position at Bell Labs when Shockley left, as the manager of the semiconductor lab. And I would leave Kirk's to come up to Stanford to teach my class, and Shockley would go back to the Quonset hut and call Morgan Sparks to say, look, here's what I'm trying to do for Stanford, and here's this guy that they think maybe can do it, and he's stuck, and can you help him? He said, well, I'll have him give me a call. So I call Morgan Sparks. Or I get back to my office after my class, and there's a note there from Bill Shockley's secretary, actually his wife, Emmy. And it says, Bill has made the call, Dr. Shockley has made the call. She always called him Dr. Shockley in public. I don't know what she called him in private, but it was loving, I'm sure. Anyway, you're to call Morgan Sparks. So I call him up. And he says, well, I'm really delighted with what Bill's trying to do to help you get a lab going, and I'm thoroughly interested in that myself. And I understand your problem to be the following. He had it nailed, dead on. Shockley had understood what I needed perfectly. He had communicated it to Morgan Sparks perfectly, and Morgan Sparks, when I called up, had an answer, had something. He said, okay, here's what I want you to do. Well, I had other things to do. I had students to, office hours and various other things to do, plus still trying to get the lab up. But he'd say, okay, try this and let me know when you've done it. And I said, well, I won't be able to do it today probably because I've got a lot of stuff, and I won't get around to it till 6 or maybe even 7. And he said, I said, call me. Call me when you've tried this, because I need to know whether it's going to work for you or not. That's commitment, and it worked. So we did get the lab running, as it turned out, and that'll put me in a fast forward here to March of 1958, when 3 announcements were made. One of them is that Fairchild Semiconductor announced its first silicon bipolar transistor for commercial purposes 6 months after leaving Shockley and 2 years after the formation of Shockley Semiconductor Labs. Gordon knew how to do that before we left. Shockley succeeded in producing 100 4-layer diodes per week. Still, all the applications were in military. And Stanford, Stephen, it's true, Stanford, this was the first lab ever made, the first device ever made at Stanford. There we are. I had a diffusion furnace, courtesy of Gordon Moore, and we had a quartz boat for putting the samples in and out of the diffusion furnace, and a dilute concentration of boron trichloride flowing through the furnace, so we would dope the semiconductor with that. And that boron trichloride went out through that stack, up through the second floor roof, and there was a little hat on top of it. So all that boron trichloride was floating out over the Stanford campus. Fortunately, we didn't poison anybody. I am obviously delighted with this result. John Linville, on the left, is looking at Gerald Pearson to see what he thinks. Well, Gerald Pearson was, among many other things, first of all, an extraordinary experimentalist. He knew what the cake should look like in every stage of the stirring without having made one. He also was the inventor of the silicon solar cell. Gerald is non-committal, to say the least. But we had a lab. It was working. So now I'll close out the conversation about Shockley. In July of 1959, Shockley, because of his having replaced his original team with an equally talented team of German and Swiss physicists and electrical engineers, succeeded in getting 4-layer diode production up to 1,000 devices a month. Still important in military applications, but volumes low. Western Electric, who had guaranteed Shockley that they were going to use the 4-layer diode, decided not to use it, and that wiped out the only major market that Shockley had. There was no, oh yeah, there are other markets here we could use this in. That was it. Shockley Labs was then sold to Cleveite, 1960, and then, thank you, Tom, to ITT, the burial ground for startups, in some ways, 1968, and the labs finally closed in 1969. Now we go to Fairchild. And if I told you the birth of Silicon Valley was when they signed the agreement with Fairchild, I want to start now getting you into how Silicon Valley grew from that point. On January 17th, 1959, Jean Herny filed for a patent on the planar process for building silicon transistors, vastly better than any of the existing processes. It made possible the high-volume manufacturing of high-quality transistors. By March 1959, Jean Herny had fabricated transistors using his planar process, and by October, all Fairchild transistors were made using the planar process. On January 23rd, 1 week after Jean Herny filed his patent, Bob Noyce files a patent on the integrated circuit. He proposes the use of the Herny process to fabricate multiple transistors on a single chip and connect them into a functioning circuit. That is the beginning of Moore's Law. You've heard a lot about the death of it, but this is its beginning. Jay Last is given responsibility to develop technology for manufacturing integrated circuits. Fairchild, seeing the enormous success of his company, exercises his option to buy them out. Each founder got $300,000, approximately $3.5 million in today's dollars. And they have now become respected members of the business community. So I won't go through naming these guys for you again. I just want to observe that this is the only time that I ever saw them in suits and ties, before or after. Then another pivotal event occurred at Bell Labs. We got accustomed to the fact that all these pivotal events are going to occur in Silicon Valley. No. John Atala and Daewon Kwong invented the MOS field effect transistor in November. Due to the ease of manufacturing, fabrication, and scaling, the MOSFET and its derivatives will permanently displace the bipolar transistor as the principal device for volume IC manufacturing after about 1975. Now we'll look at the real impetus for Silicon Valley, which has to spin out of Fairchild. The first two members of the Fairchild team to leave are Jay Last and Jean Herny. They form a Melco, a division of Teledyne, with a friendly license from Fairchild to manufacture integrated circuits for military applications. Important note here, creating integrated circuits for a major application often leads to the creation of new firms in Silicon Valley, because usually the demand is larger than one company can provide, and there are pieces of it that don't conflict with the company you're leaving. So we've learned about that and how you do it successfully and with mutual agreement. John Last and Herney are later joined by Gene Kleiner and Sheldon Roberts, which divides the original Fairchild 8 into two groups of four. And Amelco, because of Gene Kleiner, creates a new paradigm for corporate formation in which stock options are available to everybody, and you've got a very flat organizational structure. Silicon Valley. Eventually, now 5 years later, Jean Herney himself leaves Teledyne Amelco in 1967 to form Union Carbide and then Intersil Semiconductor, specializing in part in watch processors for the Swiss watch industry. Noyce and Moore leave Fairchild in 1968 to form Intel. A couple years later, Ted Hoff invents the microprocessor in 1970. It was commercialized in the next year or two by Federico Fagin, Ted Hoff, and others. And the first products were brought to market in 1971. The Fairchild 8 have now all left Fairchild. And they made new companies. Here is the Big Bang representation of Silicon Valley. At the center of it is Shockley, who formed an unstable company. Those are Gordon Moore's words, actually. And what came out of that was Fairchild. The arrows that go out from Fairchild are all the companies that spun out of Fairchild for economic reasons, interest in integrated circuits at various applications. There are 13 of those direct spin-outs there. And one of them is Intel. I don't have a pointer that can help me here, but if the horizontal axis there, or the radial axis of the circle, is in time, and so at the end of that circle is 1969 to 71, I think, 68 to 71. And if you go from there down 3 companies, you'll see Intel, a direct offshoot of Fairchild. There's AMD around there a little further. There's Amelco up to the top left at about 2 o'clock, and then there's Union Carbide and Intersil and so on. 40 companies in that group. Total revenue of that group in 1975 was a little shy of $500 million. The total revenue of Intel in 2017 was $75 billion. So a lot of growth from that group. It has become, some people say, the first trillion-dollar startup, maybe the last. Now, we turn back to Stanford. So, here's the sequel. We built the solid-state electronics laboratory. Our interests were to study basic material science, device physics, and process technology for silicon devices, and 3,5 compounds. The faculty had been started by John Linville. I helped him get going. Because there were no other universities that had labs like this, we became of interest to places that, to people that otherwise would have to, not be at a university, basically. John Mall was the first of those. He brought to us an extraordinary reputation already, and he did some wonderful things in our lab. His first PhD student was Lou Terman, Fred Terman's son, and he built an MOS capacitor and found some difficulties in keeping the threshold voltage somewhere inside 15 volts. Gerald Pearson, who had come out here before just to help me get the lab going, but as it happened, I had the lab going before he got here. Nonetheless, he was willing to join us. He and Jim Angel were hired by John Linville in 1960. Bill Spicer and Bob White were hired by John Linville in 64. Jim Meindl in 68. And Dick Swanson, Dick's out here somewhere, in 74. That is the development of a laboratory that had never been seen before. And the stuff that came out of it was just truly extraordinary. All well known. I happened to be the youngest member of the group, and so when it came time to clean the lab, sort of, well, Jim, guess what? Not quite. I want to back up a minute. I want to point out to you that Shockley invented the bipolar transistor in 1948. It was 10 years before a lab at Stanford, as it happened, would feel like the product had been developed far enough to warrant having a university laboratory. I told you that Bob Noyce invented the integrated circuit in 1959. Now here we are at Stanford in 1969, a decade later, when integrated circuits are now the dominant product in a rapidly advancing semiconductor industry. So John Linville set about again to build a laboratory. Stanford IC Lab developed process modeling tools that were and are used worldwide for IC fabrication, courtesy of Bob Dutton and Jim Plummer. High-power ICs and devices, courtesy of that same lab, and especially Jim Plummer. And special-purpose ICs, one of which was for the reading aid for the blind that John himself developed because his daughter was blind. We now had added to the EE faculty Jim Meindl. He'd already come to the solid-state lab, but now he moved and helped to start the IC lab. Jim Angel, Malcolm McWhorter, and some new guys, Jim Plummer, Bob Dutton, Krishna Saraswat, Fabian Pease. 10 years later, I told you, you all knew that Ted Hoff invented the microprocessor in 1970. 1980, a little bit outside my time horizon here, but we founded the Center for Integrated Systems. Founding it was a joint effort of Linville and Jim Meindl, myself, and Mike Flynn, whose primary appointment was in computer science, double E in computer science. That lab was dedicated to building systems where the software-hardware trade-off is critical to efficient functioning. Several of the talks you've heard today relate to that theme. 20 corporate members also participated in the research. That was another first, because it was sort of, hey, wait a minute, you can't be doing work for corporations. Well, the good offices of Bill Hewlett helped everybody understand that we all need to help this lab get going, because what's done there is going to be fundamental and we're all going to have access to it, but we cannot have access to the patents, because that way one of us will succeed more than the other. So in that lab, all the patents that were generated by the money that the industrial sponsors put in, no patent rights were asserted. The faculty now are John Linville, Jim Meindl, myself, Mike Flynn, John Hennessy, Jim Clark. John Hennessy built his first MIPS chip in this lab. The IC lab, plus the solid-state lab. So I'll summarize by talking about both Silicon Valley first and then Stanford. Fairchild and the Fairchildren, as they were called, realized Shockley's dream of creating a new industry based on silicon device technology, including a new paradigm for corporate formation, creation of a VC industry Gene Kleiner and Don Valentine, both out of Fairchild. Help support new startups that would fuel future generations of innovation. The development of a manufacturing equipment industry to serve the needs of semiconductor companies, including eventually wafer foundries around the world. The development of MOS technology that allowed very high density circuit designs. 2018, I believe TSMC produces parts, we're building 10 billion transistors per chip from one in 1959. At Stanford, Shockley's 1957 proposal for Stanford and John Linville's long-term leadership of the department, of the lab, first the solid-state lab and then the department, led over time to the creation of 3 major laboratories based on innovations in industry. They didn't come from Stanford, they came from industry. The transistor, the integrated circuit, microprocessor. And in 1962-63, the first year-long undergraduate course on semiconductor was offered at Stanford. Jim Harris was in this class. It is what is now known as EE, or was for a long time, known as EE 111, 112, and 13. Then I can't remember what it was. Maybe Jim does. Thank you for your attention. Any questions, disagreements? Excellent. Thank you. Sorry.
You got one. You got one.
Oh, I should have said, and I didn't say, and she'll be embarrassed by this, that this slide deck has been created for me by the patient, brilliant Rochelle Mozaleski, who's standing up over there. Give her a hand. And there was a question somewhere.
Yeah, I just had a question on when the team left Shockley, was there any sort of patent dispute or IP? I was a little surprised that there was no mention of there being lawsuits and things thrown at the...
Shockley did have a lot of patents. A lot of patents had been awarded to the Shockley semiconductor. They were owned by Arnold Beckman. And the thing is that when somebody goes off to do something, you can't, if it's stuff that they've learned and they're going to use it in a somewhat different situation, then there's no indentured servitude here. So if you're not going to use a patent, then Shockley was already a licensee of Bell Labs because they had the basic patent on the transistor. And when there were patents issued to us at Shockley, all of Shockley, but Arnold Beckman, since he owned the company, was in charge of following up on that, litigating if necessary. So he comes up the day after the Fairchild guys have signed the agreement with Fairchild to say, look guys, I'm going to stop this. Actually, he'd made a decision earlier when he backed Shockley twice, and he was really concerned about the fact that now all of a sudden he's going to take advantage of these guys. So his ethical sense, I must say, is what led him to say, look, I failed. Shockley failed. And I don't own much in the patents of this company. There's not much. I was going to sue these guys for it, to say, you can't do this. You've got to be me. Well, they'd already signed with Fairchild, and Beckman had had his chances, so he never prosecuted. Then, of course, all the inventions that the planar patent and the integrated circuit patent, those two drove Silicon Valley for a very long time. Those were proper Fairchild patents. When Jay Lass left, Jay and Jean Herney left Fairchild to form Amelco, it was on a friendly basis. They negotiated a license with Fairchild to get rights to manufacturing for military applications, where all the conditions were different. The way you did it and the radiation sensitivities, all that other kind of stuff were all important that Fairchild didn't want to get involved with. So that's how a friendly license was set up. That's true most of the time in that development of Silicon Valley. Friendly licenses, not totally friendly all the time, but anyway, I hope that answers your question. Any more out there? Okay, thanks again.